Okay, so thanks for everyone for coming back for the second talk of this morning, which is Aleksandra Huczek from the University of Krakow. Who's going to talk about a unified approach to Wolff-Denjoy.
Thank you very much. Good morning. At the beginning, I would like to thank the organizer for the possibility that I can give them a talk. And it's a great pleasure for me because it's my first talk in my life. I am a PhD student and my academic supervisor is Professor Andrzej Wysocki. We consider a Wolff-Denjoy type theorem in different contexts, and today I would like to present the further results of our work. The starting point to my research is, of course, the classical Wolff-Denjoy theorem, which was formulated in 1926. This theorem describes dynamics of iterates of holomorphic self-mapping on the unit disk. In other words, if F is a holomorphic self-map of the unit disk without a fixed point, then there exists point C belonging to the unit circle, such that the iterates Fn of F converge locally uniformly to C on the unit disk. This theorem has been generalized over years in different directions. I will give a few examples. In complex variables, the first results are due to Airy and Abate. Verdon studied the Wolff-Denjoy type theorem for one Lipschitz mappings on domains with Hilbert's metric, and this theorem was further developed by Abate and Reisi, Kobayashi, Carlson, Noskov, and Nussbaum, and all. Conclusions for one Lipschitz mappings on domains with Kobayashi's distance was presented by Buzyńska. What am I going to talk about today? This is the plan of my presentation. Firstly, I would like to present necessary definitions and lemmas. Next, I'm going to present the Wolff-Denjoy type theorem in proper geodesic spaces. Next, I would like to present the Wolff-Denjoy theorem in the case of strictly convex domains in finite dimensional spaces. And at the end, I'm going to present the Wolff-Denjoy theorem in case of compact mappings in infinite dimensional spaces. Let's start at the beginning. I will focus on necessary definitions. We consider a metric space YD. A curve is a geodesic or geodesic segment if for any T1, T2, the distance between sigma of T1 and sigma of T2 is equal to the distance between T1 and T2. Moreover, if every 2 points of Y can be joined by a geodesic, we say that Y is a geodesic space. A map F is called non-expansive if satisfies the Lipschitz condition with constant equals 1. A tool needed for investigation the dynamics of non-expansive mappings is the notion of horrible. We consider 2 types of horribles. The small horrible of center C belonging to the boundary of the space, posit 0 and radius R is defined by a set of y's such that limit superior of the difference between the distance between y and w at 0 is less than or equal to R. And by analogy, the big horrible but a set of y's such that the limit inferior of the same difference is less than or equal to R. Unfortunately, we cannot show that in proper geodesic spaces, small horrible is always on empty. We cannot show it, but we show that big horrible is always on empty. What is in the following proposition? We suppose that YD is proper geodesic space satisfying axiom 1. What axiom 1 means, I will tell you on the next slide. Z0 in Y, R is a number, and C is belong to the boundary of the space. And then the big horrible is non-empty. Let's see a brief proof. We fix it 0, C and R. In all our results, we will always assume that metric space satisfies the axiom 1. What it means? Axiom 1. The metric space is an open dense subset of compact metric space Y by the bar, whose relative topology coincides with the topology of Y. And for any W, if Xn is a sequence in Y converging to the point on the boundary of the space, then the distance between Xn and W diverges to infinity. And it follows from axiom 1 that in this case there exists a sequence Yn converging to the point on the boundary such that the distance between the sequence Yn and Z0 diverges to infinity. So we can assume that the distance between this sequence Yn and Z0 is greater than R for any natural number. And now we consider a geodesic segment Z0 Yn and the point Xn lying on it such that the distance between Xn and Z0 is equal to R. Then by properties of geodesics, we can write down that the distance between Yn and Z0 is equal to the sum of these two distances. Okay, next, since Y is proper, the closed ball is compact, and hence there exists a subsequence of sequence Xn converging to some point belonging in the space Y, such that the distance between X and K and Z0 converges to R. Therefore, we have the first equality is by convergence X and K to X, and the second inequality is from it. It's sufficient to take small r greater than or equal to minus big R, and thus we get that X belongs to the big parabol, which ends the proof. We cannot improve this proof and show that in the same way the small parabol is non-empty. Okay, now we will consider the following properties of metric space called axioms. I repeat again the axiom 1 because it's crucial for us. The metric space is YD is an open dense subset of compact metric space Y bar to bar, whose relative topology coincides with topology of Y. And for any point W in Y, if Xn is a sequence converging to the point on the boundary of the space, then the distance between the sequence Xn and W diverges to infinity. Axiom 2. If you have two sequences, Xn and Yn, converging to two distant points in the boundary of the space, and we have point W inside Y, we have that the distance between Xn and Yn minus the maximum of distances between Xn and W and Yn and W diverges to infinity. Axiom 3. If Xn and Yn are two sequences in Y again, Xn converges to Xi, which belongs to the boundary of the space, and for some W, the distance between Xn and Yn minus the distance between Yn and W diverges to minus infinity, then Yn converges to Xi too. And the last one, axiom 4. Again, we have two sequences Xn and Yn. In Y, Xn converges to Xi, which belongs to the boundary of the space, and for any natural numbers, the distance between Xn and Yn is bounded for some constant C. Then Yn converges to Xi too. Okay, it's possible to show that axioms 1 and 2 imply axiom 3, and axiom 1 and 3 implies axiom 4. In one of Verdon's works, you can find the Wolff-Denjoy type theorem for metric spaces satisfying axiom 1 and the following condition. The following condition for two sequences converges to two distinct points on the boundary of the space and any W inside Y. We show that the assumptions can be weakened to the following condition. It means to metric space satisfying axiom 1 and axiom 3. Okay. We have got everything what we need to formulate the Wolff-Denjoy theorem in proper geodesic spaces. I repeat the axiom 1 on the top of the slide for the record. And we have the theorem. Let YD be a complete locally compact geodesic space. The Hoplinov theorem states that metric space proper even completely locally compact. So we can say that let YD be a proper geodesic space satisfying axiom 1. And for any two sequences in Y, Xn converges to eta belonging to the boundary of the space, such that the distance between these two sequences X and Yn is bounded for some constancy. We have that Yn converges to eta 2. In other words, we have a metric space satisfying axiom 1 and axiom 4. Next, we suppose that for every zeta and z0, the intersection of Horobos closures consists of a single point. And if F is an expansive self-mapping without bounded orbits, then there exists point C belonging to the boundary of the space, such that the iterates Fn of F converge uniformly on bounded sets of Y to C. I would like to present the sketch of the proof of this theorem. The following lemma plays the key role in this proof. We suppose that F is non-expansive self-mapping, and there exists point C, such that for every Z0, for every real radius R and a sequence of natural number, there exists point Z in this space, and a subsequence of An such that iterates F, A, K, and K of Z belong to the big horobol for every natural number K. Moreover, if the space satisfies axiom 4, we have that C belongs to the intersection of big horobol's closures. By assumption, we have that intersection of big horobos closures consists of a single point, but on the other hand, we have this lemma. So we can write down that the intersection of big horobos closures is the one point Z, and the only element is C. Okay, we fix Y and select a subsequence F, A, N of Y converges to eta, which belongs to the boundary of the space, and we know that C is equal to eta. We fix R and use again the same lemma. All assumptions are satisfied, so we can write down that iterates F, A, and K of Z belong to the big horobol. Since F is non-expansive mapping, we can write down the last inequality. And since F, A, N of Y converges to eta, and the distance between F iterates F, A, and K of Y and F, A, and K of Z are bounded, it follows from axiom 4 that F, A, and K of Z converges to eta 2. Okay, now since the limit of the elements of the big horobol must belong to the closure of big horobol for any real radius R, we can write that eta belongs to the closures of big horobols, which is one point set. So we have that C is equal to eta. And since a subsequence was chosen arbitrarily, we have that F and Y converges to C. What ends the first part of the proof. In the second part, we prove a uniform convergence on bounded subset. We suppose, on the contrary, that there exists open neighborhood of C, set K and sequence Yn such that iterates Fn of Yn not belong to to you for every n. By non-expansivity of mapping F, we have that this inequality that the distance between nth iterates of yn and y are bounded. Now, since fn of y converges to c, and the distance between nth iterates is bounded, we have from axiom 4 that iterates fn of yn converges to c2, and it's a contradiction. It's a contradiction. Okay. A natural question is it possible to modify the assumption of the above theorem? The answer is yes. For this purpose, we will consider the following lemma. Suppose that YP is proper geodesic space satisfying axiom 1, and for all two sequences xn and yn, xn converges to eta, and for some w, we have this difference diverges to -infinity. We have that yn converges to eta 2. In other words, the space satisfying axiom 1 and axiom 3. And if z0 in y and zeta is in boundary of the space and r is a number, then we have that intersection of big Horobos closures is the one-point set, and the only element is zeta. Combining this lemma and the above and previous Wolff-Denjoy theorem in proper geodesic spaces, we have our main result of this section. Let YP be a proper geodesic space satisfying axiom 1 and axiom 3 written with sequences. And if F is an expansive cell mapping without bounded orbits, then we can find the point C belonging to the boundary of the space such that iterates Fn of F converge uniformly on bounded sets of Y to C. Okay, the next step is to apply our results to case of bounded strictly convex domains in finite dimensional spaces. In this part of the presentation, we will unify Bernoulli's and Wojcicka's results regarding Kobayashi's distance and Hilbert's metric. In our results in this section, we will always assume that we have a metric space whose topology coincides with the norm topology. Okay, the main theorem of the previous case satisfied axiom 1 and axiom 3. Firstly, we would like to transfer axiom 1. For this purpose, we will consider the following lemma. We suppose that D is a bounded domain of finite dimensional vector space, and DD is a complete geodesic space. Then DD satisfies axiom 1. And we see a very brief proof of this lemma. We suppose that Xn is a sequence, converges to the point in the boundary of D, and we show that the distance between Xn and Y diverges to infinity. So on the contrary, we suppose that there exists a subsequence such that the distance between x and k and y is bounded for some constant c and for some y in D. Since D is a locally compact space, it follows from Wolff-Denioy theorem that D is proper and that the subsequence there exists a subsequence x and k l, which is converges to some point x0. But on the other side, the topology of D coincides with the non-topology, and we have that the subsequence x and k l converges to x0 in norm, what is a contradiction. What is the contradiction? Okay, next we would like to transfer third axiom, and the next lemma is valid for any metric which satisfies the following condition, which is equivalent to the convexity of balls in D. We suppose that D is convex and bounded domain. Then we have that for any points x, y, and z, and for any s, the distance between any point of segment sy and point z is less than or equal to maximum of distance between x and z and y and z. And we have the lemma. We suppose that D is bounded, strictly convex domain of finite dimensional vector space, and D satisfies condition C. There, space D satisfies axiom 3. And again, we see a very brief proof of this lemma. We suppose that we have two sequences x and yn. Xn converges to C, which belongs to the boundary of the space, and for some w, we have that this difference diverges to minus infinity. On the contrary, we suppose that the other sequence yn converges to a point on the boundary, but eta is not equal to C. Since D is strictly convex, we have that every point of the segment C eta must belong to D for some s. Then we have the first inequality is from triangle inequality, and the second inequality is from condition C. Since the difference between these 2 points converges to 0 in norm, and topologies D and D bar coincide on D, we have that the distance between the point on the segment C eta and the point W diverges to infinity, what is a contradiction, since we assume that this point lies strictly inside D. So it's a contradiction. Combining these two lemmas and the main Wolff-Denjoy theorem for proper geodesic spaces, we have the main theorem of this section. We suppose that D is bounded, strictly convex domain of finite dimensional vector space, and the D is a complete geodesic space satisfying condition C, whose topology coincides with the norm topology. And
can you please go back to the previous theorem?
Previous theorem, yes, of course.
The other one, the lemma.
The lemma from axiom 1 or axiom 3?
No, next one.
Yeah. Okay, and we suppose that there exists point C belonging to the boundary of the space, such that the iterates Fn of F converging only on bounded sets of D to this point C. The next step is to apply our results to the case of bounded strictly convex domains in n-dimensional real or complex spaces with respect to different metrics. Now we consider a closed normal cone with non-empty interior in a Banach space. And we say that y dominates x even only if exist alpha and beta, real numbers alpha and beta, such that alpha y is less than or equal to x and x is less than or equal to beta y. This notion yields on K an equivalence relation. We say that x in relation in y even only if x dominates y and y dominates x. And for any x and y's such that x in relation in y and y is not equal to 0, you can define big M and small m, big M as an infimum of betas greater than 0, such that x is less than or equal to beta y, and small m as a supremum of alpha is greater than 0, such that alpha y is less than or equal to x. And the Hilbert pseudometric we can define by a logarithm big M over small m, and the Thompson metric as a logarithm of maximum of big M xy and big M y x. The following lemma shows that Hilbert's metric satisfied the inequality with maximum. In other words, it was condition C. And in the same way, we have formulated the counterpart for Thompson's metric. And then we can formulate corollaries. This corollary is from Hilbert's metric. If we have fixed on free non-expansive self-mapping, then we can find the point on the boundary of the space such that the iterates f and of f converge from the unbounded sets of D to C. And in the same way, we have the counterpart of corollary for Thompson's metric space. Okay. Now let's say about equally interesting result for Kobayashi's distance. In similar way, we can formulate this lemma, which shows that Kobayashi's distance satisfied inequality with maximum, or in other words, condition C. And we have the last corollary of this section, the Wolff-Denjoy theorem for spaces with Kobayashi's distance. Okay, we'll go to the last section, in which I will talk in a few words about the Wolff-Denjoy type theorems in infinite dimensional spaces. In this case, we need to slightly modify the axioms and introduce several definitions. Let's start from axioms. Axiom 1 prime, the metric space YT is an open dense subset of metric space Y bar D bar, whose relative topology coincides with the metric topology. And for any W, if Xn is a sequence in Y converging to the point of the boundary of the space, we have the distance between X and W diverges to infinity. What is the difference between axiom 1 and axiom 1 prime? In axiom 1 prime, the compactness of Y bar is not required. And we have axiom 3 prime. We have two sequences, X and Yn in Y. Xn converges to C and Yn converges to eta. 2 points belong to the boundary of the space. And if for some W we have the following condition, then eta is equal to C. And axiom 4 prime. And then we have two sequences X and Yn. Xn converges to C and Yn converges to eta. And for some constant C and for any natural number n, we have that the distance between X and Yn is bounded. Then we have that eta is again equal to C. Okay, we need to consider a wider class of quasi-geodesic metric spaces. A curve sigma is called lambda kappa quasi-geodesic if there exists lambda greater than or equal to 1 and kappa greater than or equal to 0, such that for any T1, T2, the following condition is satisfied. And we say that metric space is lambda kappa quasi-geodesic if every pair of points can be joined by lambda kappa quasi-geodesic. And the last one definition, a mapping F is compact if the D bar closure of F of Y is compact in Y bar D bar. Okay, the next theorem is a counterpart of the Wolff-Denjoy type theorem in infinite dimensional spaces for quasi-geodesic spaces. we suppose that while V is a one kappa quasi-geodesic space satisfying axiom 1 prime and 3 prime written as sequences. And if F is a compact non-expansive self-mapping without bounded orbits, then there exists point C belonging to the boundary space such that the iterates Fn of F converge uniformly on bounded sets of Y to C. The proof of this theorem is by analogy to the case of proper geodesic spaces. We remember that these 2 points was from an important lemma. We have, in this case, we have a counterpart of this lemma. What is the difference? In this case, we suppose that we have a 1 kappa quasi-geodesic space, and F is compact, non-expansive mapping. But the rest of the lemma is the same. And since F is compact mapping, we can select a subsequence, and the rest of the proof is essentially the same. Okay. Now we would like to formulate, in this case, for infinite dimensional spaces, the Wolff-Denjoy type theorem satisfying condition C, in other words, inequality with maximum. And for this purpose, we'll consider the last lemma. We suppose that D is strictly convex domain of one X space, and VD is a metric space satisfying condition C, whose topology coincides with the known topology. Then the metric space D satisfies axiom 3 prime. The above lemma and the Wolff-Denjoy theorem of this case immediately goes as this theorem. We suppose that D is strictly convex domain of one space, and D is lambda kappa quasi-geodesic space satisfying axiom 1 prime and condition C. If F is compact, non-expansive self-mapping without fixed point, then there exists point C belonging to the boundary of the space such that the iterates F and F converge uniformly on bounded sets of D to C. And we have again 2 corollaries for Hilbert metric and for Kobayashi's distance. In this case, we have 2 corollaries. And that brings us to the end of my presentation. Thank you very much for your attention.
Next question online. No.
Hello, can you hear me?
Yes, we can.
Yeah. So could you just go back 1 slide?
Which one?
Yeah, that's the one. Yeah, that's the one. The entire slide. So I couldn't take this down. So could you remind me, if I remember correctly, in one of the corollaries, it is condition C that is satisfied, and in the other corollary, axiom 1 prime is satisfied. Do I have that right?
I think that it's true that axiom 1 prime is satisfied also.
So is it axiom 1 prime satisfied for both the cases?
I think yes, but now I'm not sure.
Yeah, because there was also this other element, right, which you called condition C.
I don't know at this moment.
Okay, so
Yes.
Okay.
it is, right?
Yes.
It is yes for both, correct? Yeah, so axiom 1 prime is true, but condition C is also true for both cases, yes?
Yes.
Okay, and I had a second question, which is, this is outside of the strictly convex domain in Banach space setting. Outside of the Banach space setting, do you have any example of a metric space that is not a proper metric space, but is a one kappa quasi-geodesic space and satisfies axiom 1 prime? So do you have any examples outside of a Banach space setting?
No, I understand your question, but no, I haven't got the example at the moment.
Okay, right.
No, sorry, I don't.
Sure, no problem. Yeah, thank you so much.
Thank you very much.
Any other question online?
Yes, I have some questions. Sorry.
Okay, Bart.
I can't seem to raise my hand anymore. Yeah, so maybe going back to this Thompson metric case. So this, yes, this one. So first of all, actually, this is true without strict convexity, not with converging to a single point, but converging to a convex phase of this, the bounded of the domain. But it's quite unnatural to actually have a set D, which is actually left invariant, which is bounded and strictly convex, which is where you have a non-expansive map, which is non-expansive with respect to the Thompson metric. So actually, the normal mappings are always defined on a cone. So your D typically is a cone. And so I personally don't know any example of a non-expansive mapping with the Thompson metric where your D is actually bounded domain, convex domain. But maybe if you have some.
No, I don't know. Sorry,
So
it's very fresh for me, and I'm not sure.
Okay. So Bas, just repeat for me. So I got
mean,
your point about.
I mean, it's not.
Yeah, but you talked about a fixed, right? That is to say, you talked about some sort of a non-empty invariant set. Could you repeat what you said? This is interesting.
Okay, so maybe if the speaker could go back to the case where she defines the Thompson metric.
Definition, yes.
Yeah. So the definition. So yes. So here you see this metric. I mean, this at first sight looks a bit archaic, but actually it's not at all. This Hilbert metric is actually the Birkhoff version of Hilbert's metric. It's a pseudo metric because it's a metric between pairs of rays in a cone. Sure. However, if you projectivize it to a slice of the cone, you get exactly the Hilbert metric as you're used to.
Right.
Now you can also make a metric by taking the maximum of these two, rather than you could have also taken the sum, which is the same as above. But then you get a proper metric on a cone, on the interior of a cone. This works perfectly in infinite dimensions anywhere. If you have an interior of a cone in a vector space, you can put this metric on it. Okay, and the natural mappings that are non-expansive are actually linear mappings, but there are also many non-linear mappings that are non-expansive. But your domain is typically the whole cone, the interior of the whole cone. And then the boundary of the cone actually lies at infinity. And also if you drift off in norm to infinity, you're actually going to infinity in this metric. Okay. So, yeah, typically, so there's a paper, which I'm sure the speaker is aware of, which I wrote with Roger Nussbaum and Brian Linz and Martin Wortel which appeared in Journal d'Analyse, where we actually do Denjoy-Wolff theorems for this Thompson metric on the cone. And it doesn't really matter as long as the norm of the orbit stays bounded in the cone, and it is, well, there's some compactness condition on the map. You actually, independent of the geometry of the cone, you go, the whole attractor lies in a closed, convex subset of the boundary of the cone. Okay, and this is independent of any geometry, which is actually remarkable. And also, this leads to also some results for Hilbert metric non-expansive maps, classes of those, where also independent of the geometry of the cone, you get convergence to a convex subset in the boundary. Yeah. So
when you say convergence to a convex subset, do you mean the convex subset is a cluster set? Is that what you mean?
I'm just saying, normal, the statement is it goes to a single point in the boundary.
Right.
That you cannot hope for in general.
Sure.
But you can say, is there a phase or a convex subset in the physical boundary where all the limit points lie?
So set of all limit points sits inside this.
Sits inside this convex subset.
Right.
Or a phase of the domain. Yeah.
Right.
And that you can prove in these settings. Yes.
Right. Okay.
Yeah. Okay.
So the audience has a question, because I don't want to stop you, but it looks like a private discussion. So maybe we ask also the audience if there is a question.
Thank you very much.
One second. Is there any question here as well?
Before asking the question, I want to thank you for this very nice talk. It was very nice, and we start totally the first talk is good. So thank you very much. I have just a tiny stupid question. So have you already started to work trying to take out condition C, for example? Do you think
I don't forget about it. No.
Thank you.
Yep.
Okay, and two questions. But first of all, I thought it was a very interesting talk. Started thinking about things that can be done with this kind of approach. And do you have, the whole approach, the results you described just in one point, the fact that you are working with strictly convex domains. Do you think you have started thinking about it? Whether it is possible to get, of course, not exactly this result, but some results also in the weakly convex case?
I didn't thought about it, but I think it's a very interesting question, and I have to talk about it with my supervisor. Yes.
Okay, and the second question is a silly question, so I apologize in advance. In a few of the statements, you said something like, assume that the metric space satisfies action 1 or 1 prime, and then you list a definition which mostly meant that you're assuming that it also satisfies action 3, for instance.
Yes.
Is there any reason why you stated it in this way instead of just saying assume that it satisfies action 1 and action 3?
I think it's easier for us to write in this form. Yes.
Okay, so it was just a matter of exposition, it's not matter.
Yes.
Okay, thank you.
Thank you.
We are what you said before. Actually, condition C appears in the Wolff-Denjoy geometry. It's called as secretness. And I believe it's one of the weakest forms of find of negative curvature. So this is not a simple assumption. Instead, for instance, in the geometry are not line attention, but the likeness. So this is important, for instance, in quantum logic, just an assumption. But it shows that the polynomial is different. The topological function. You need this is not something we can do. I think it's crazy. So maybe we can try again, and because it was
Nice talk. Thank you very much.